Yes, so the first thing is an addendum, which, let's see, does it work with animations? So I didn't make them. To illustrate, so let me say more or less quickly. Here in this one, in the bottom row, what you are seeing is the geometric behavior that on the Poincaré disk has a hyperbolic Morris transformation, preserving D bijectively, an elliptic Morris transformation, preserving D bijectively, which, as you, and a parabolic Morris transformation, again preserving D bijectively. More precisely, what you are seeing here is like on the one hand, the behavior of the action of the positive powers of the given Morris transformation on several orbits, and on the set of Apollonius circles, which, as we know, are that family is permuted. And here you can see that there is this repulsive point, which is one of the fixed points, and the attractor, which is the other fixed point. One feature is that this if you think about it, this more or less resembles the Euclidean translations. Well, the elliptic one, again, what you are seeing is the behavior of the positive powers of the elliptic transformation on several the orbits under the positive powers of several points. Yeah, and several points, let's say, lying on one of the common circles. And well, I'm not going to repeat what I've said many times. This, as you see, the elliptic ones do look like rotations of the hyperbolic plane. And the parabolic one, which is kind of it looks like a limiting in between, like a limiting picture in between the behaviors of these two. And the same thing, we can see the behavior on you see the orbits of several points of the orbit, the behavior on several points of the positive powers of the parabolic transformation, where that set of points of which we take the orbit are always aligned on a circle, on an Euclidean circle passing through the point, which is a point at infinity, which is at the same time a repulsor and an attractor. Okay, so and I do like recommend you to visit this site. I mean, it's a very nice site. The link you can see in the notes. So that's the first animation. The second one is a short video. Really find it beautiful. The third one is a similar one. And it's not the South Pole, it's the origin. The next video, it's a little bit a long one. It's quite beautiful, I would say. It's a bit long, so maybe this video let me leave it for like if I have enough time at the end, or you just watch at home. The fourth one is really beautiful, but it's like 5 minutes long. In the upper half plane, yes, basic construction, see, Faraday diagram. So what you are going to see, so maybe I'm going to write 25, is the first 25 steps in the recursion of, like first just the integers and infinity with the consecutive integers joined, and each integer connected to infinity, and then at each step add the naive additions between things that are already adjacent, yeah, and the new edges to these ones. Draw, I think it's this one. Yeah, so that's, and of course, what you are seeing, since we said that we draw the edges actually as geodesics, so these are actually Farey edges. So it's like a graph whose edges are geodesics in the hyperbolic plane. Looks exactly like this. One thing to note is that it looks like actually somehow in the end we triangulate the upper half plane. I mean, at least it looks like after the whole process, if we let the whole process go to infinity, you know, and we take the complement in U of all the geodesics that appear as edges of the Farey diagram, the connected components of that complement are all ideal triangles. This we would have to prove, right? Because somehow, how do I know that in some, let's say that I don't know, like 20 million steps from now, there is not going to be an edge connecting like this point to some other point, let's say here, so that one obtains a crazy edge crossing all of them, right? I mean, somehow it requires a proof. Okay. So this is it. So let me go back to the notes.
Sorry.
Yes.
Regarding the geodesics of the hyperboloid, you say that given any 2 points, if you take the plane that cuts through those 2 points and you're reaching, then the geodesic is the intersection.
Yes.
So even if they're at the same height, let's say, so you have to go through the focus.
Yeah, through the
vertex of the hyperboloid to.
Yes. Yeah. So yeah, it's not like this. Yeah, no. I mean that. I mean, of course you can, but it's not the shortest.
Yeah. Sure,
yes.
Okay, sure.
Yeah. Yeah. Yeah, and one can prove it directly using just the differential geometry of the hyperboloid. Yeah. But I didn't do it for this course, but it can be done like directly. Yeah. So I'm going to start today with something that looks like that may look like completely disconnected from what we have been talking about. And it's just the fact that we have known forever, which is that Q is dense in R, which is, you know, like let me draw the real line. Yeah, and then take an irrational number, say alpha, and what is it? If you give me a non-zero positive integer q, so given q, you know, something I know is that alpha is between 2 integers, right? This I know. Let's say, I don't know, n and n plus 1. Yeah, and okay, and this is independent of q, I know. But if they give me a positive integer, I can partition the interval between n and n plus 1 in q equally distant q subintervals of length 1 divided by q. So let me do that. Etc. Where here each of these is of length 1 divided by q. And what? And I know that alpha is always between two of them, right? And then let's between two of them, yeah. And so let's say I don't know, p divided by q, and this would be what I think it's p plus 1 divided by q. But the fact that it's between the two of them means that whatever one of the two, that one of these two is a distance less than 1/2 of 1 over q from alpha. So yeah, and this is what we have known forever. I mean,
maybe we need n on top.
I'm sorry. We need
plus n. Plus n. Well, okay, yeah, it's not good.
What do you mean plus n? It's the distance. Yeah, because the distance, the length of the subinterval is 1 over q.
Yes.
Yeah.
Sorry.
Yeah, and the fact that it's strictly less is because alpha is irrational, so it cannot be exactly in the half. If it were exactly in the half, I would have to put this, but then alpha would not be rational. Okay, and then this I know that it looks it's like kind of why I'm talking about this. So I hope to be able to come back to this. So again, the Faraday diagram. This is just a reminder of how the naive addition is defined. That the naive addition is in between the two given. If they are rational, it's always in between the two given rational numbers. Let me introduce also the naive subtraction, which is, if you give me the two reduced fractions, well, what could be the naive subtraction? So just this one, right? And then just with the caveat that the denominator could be negative, right? And a priori, I don't yet know that this is a reduced expression for this rational number. Right? I mean, this one is reduced, this one is reduced. A priori, I don't yet know that this one is reduced. Not only because I don't know whether a priori whether these two are coprime, but also because this may be negative, or even 0, right? If b and d are equal, this could be 0, in which case I'm talking about infinity. Which is the case, for instance, if these two are consecutive integers, if they are integers, the naive subtraction is infinity. Okay. Reminder of the recursive definition, which is, again, we start with just the integers as vertices. Consecutive integers are connected. There is an edge between any two consecutive integers, and there is an edge between each integer and infinity. And then we start taking naive additions, naive sums of things that are already connected, and connect to the new ones. Right? If two things are connected, add the naive addition as a vertex and connect the two given vertices to that one. Which we saw already an animation. The Faraday diagram is what we obtain in the limit. Okay, so this is just a reminder of how the process goes. Yeah, so this is only reminder that we draw the Faraday diagram by drawing the edges as geodesics in the upper half plane, or in the hyperbolic plane, and then we were in the non-recursive description, which said that I mean, at this moment, I don't yet know whether in the limit process every rational number occurs as a vertex of the Faraday diagram. I don't yet know this. And we were in the process of proving that if you give me two vertices of gamma, written as reduced fractions, they happen to be adjacent. So there happens to there exist an edge connecting them, or connected by a Faraday edge, if and only if the associated determinant is plus or minus 1. And we proved one implication by induction. I'm not going to repeat the proof, just that during this induction, what we did was label all the edges of the Faraday diagram with matrices. Yeah? So here, maybe let me go back to see. Yeah, here is the labeling. What did I do? Sorry. Yeah. Right. Then I just briefly repeat that in the inductive step, assuming that these two were already connected by an edge, labeled with this matrix. Sorry. Every time an edge was added, we labeled the corresponding edge with this matrix, where we put the first column is given by the larger rational number. Yes, and then we investigated how in the inductive step this labeling function works in the inductive step, and then we saw that then for this new edge in the inductive step, the labeling is this one, and similarly with this one, by definition. And why did we do that? Because, and so maybe this, let me also copy this here. We did that because now we want. I mean, in the first direction, in the first implication, we showed that if two vertices are adjacent, then the determinant is plus or minus 1. And now we want to show that if the determinant is plus or minus 1, then there is an edge between the two given vertices. So we take two vertices with the property that the determinant is plus or minus 1. And of course, these two vertices are different because the determinant is plus or minus 1. If they were the same, the determinant would be 0. Okay, so they are different, and they are written as reduced fractions, so that the denominators are both positive. And so I can simply take the one with the smaller denominator. Yeah? Now, if that one is 0, then of course delta cannot be 0, because then otherwise the determinant would be 0. Yeah. But then if beta is 0, then alpha divided by beta is infinity, and the determinant is just alpha delta, which is plus or minus 1, which tells me that then how to say that alpha delta is plus or minus 1, but they are integers. So delta has to be 1, because I know delta is positive, and delta by something else is plus or minus 1. So delta is 1, but delta being 1 means that gamma divided by delta is an integer, which means that one of the two given vertices then is infinity, and the other one is an integer. And for those, we know by definition that there's an edge connecting them. So in this case, we are done. What happened was actually that in this case, we were actually in the beginning of the recursion. Okay. And now the idea then is going to be that in the arbitrary case, when beta and delta now are arbitrary but satisfy this, to do something that decreases the maximum of them, so that I can say, okay, if the determinant is plus or minus 1, then I can do something to decrease the maximum of them, and then decrease that maximum until it becomes 0, and then I know that it's two things that are connected, and then in the process, if I apply now the reverse process, it's going to be the naive addition, so connected, naive addition, so connected, naive addition, so connected. So the things I started with connected. So somehow that's and that's the idea. So if beta is different from 0, what I do, since I'm assuming this, I subtract the smaller from the bigger. So what I do is I take this one, which, if you think, actually corresponds to the naive subtraction. I mean, the thing here is precisely what corresponds to gamma minus alpha, delta minus beta. So I'm actually applying naive subtraction. And then I notice, I mean, of course, the determinant of this one is, of course, plus or minus 1, because I just added I just subtracted from one column the other one, right? So the determinant didn't change, or just computed directly. And this one, since we made decrease the maximum between beta and delta minus beta, because by assumption delta was the maximum, this one satisfies that either this one is 0 or the maximum is smaller. One of the two. I mean, yeah, beta is less or equal than delta, so this one could be 0. And yeah, so either this happens, or if this is not 0, then definitely the maximum between this one and this one is now beta. Yes, which means that the maximum decreased. Because if this is not 0, then it's because the maximum was delta strictly bigger than beta. And after the operation, the maximum is beta strictly smaller than delta. Okay, anyway, so I arrive at either these two, not those two, I would say these two connected by an edge, like this, which would be in this case if delta is equal to beta. So I mean, two quotients, right, connected by an edge, or this. So okay, in the first case, these two are connected by these two numbers are connected by an edge, and their naive addition is this one, which then gives me, these two connected by an edge, but then both of them connected to the new one. Okay, and I wanted these two to be connected, so I'm done. Otherwise, this happens, and then I just apply, Fermat's non-infinite, how do you call it in English? Not infinite decreasing. I forgot the name in English. Or if you want, modified induction, to deduce that alpha divided by beta and gamma delta are connected by an edge. So and actually are connected by an edge. Yes, but I forgot to say something, which is that actually, you see how many steps do I have to go back in order to obtain one of them equal to 0 under this process of subtracting the smaller from the bigger. Well, at most, beta times delta times, which means that this is not En, this is Vn. That actually I can exactly say V is the no, it's the edges. Sorry, it's not the vertices, it's the edges. Which I can actually say that this edge is definitely constructed in at most beta times delta times, in at most beta times delta steps in the recursion. Yeah, non-infinite descent principle of Fermat. Yeah. Okay. So this is really nice. Two given vertices are adjacent if and only if the determinant is plus or minus 1. But you see, I can actually analyze a bit further this argument and notice that I didn't even need them I didn't need to suppose that they were vertices of gamma. I just needed to know that the determinant was plus or minus 1 to be able to apply this process and conclude that, you know, I can go back by subtracting the smaller from the bigger, go back to something with the denominator 0 and an integer, so connected, and then actually they vertices of gamma, and then come back and then say, okay, vertices of gamma connected. So this means that given a rational number, as long as I can find another rational number such that the determinant is plus or minus 1, both of them will be vertices of gamma. But for a rational number, I can always written in reduced fraction, I can always find such other rational number because because these two are coprime, so there's a z linear combination of them equal to 1, and then I just arrange that as if that it was a determinant. So it's quite easy. So the Faraday diagram actually satisfies that one actually covers all rational numbers. Every rational number occurs as a vertex. So no strange things happening. And moreover, if I have two rational numbers adjacent in the Faraday diagram, so that this determinant is plus or minus 1, then for instance the determinant of this one against the naive addition is also plus or minus 1 because they are because if these were connected, then these are connected in the Faraday diagram. So the determinant is plus or minus 1, which means that if I just consider the expression of determinant plus or equal to plus or minus 1, it gives me a z linear expression of this one and this one, of the numerator and denominator, to plus or minus 1, which means that these are coprime. These are already coprime, which means this is already a reduced expression for the naive addition. And similarly for the naive subtraction, because that's actually what we used to be able to force the descent. Yes, okay, of course, provided I'm really subtracting the smaller from the bigger. If I happen to take the naive subtraction naively, well, if this one is negative, I really have to if this one is negative, I really have to just multiply by minus 1 top and bottom. Okay. Yeah. The naive subtraction becomes important becomes important because it allows to do the descent, but also I hope it becomes it becomes also clearer why the naive subtraction is as important as the naive addition. Yeah. Okay. Yeah. Some nice exercise. Yeah. So maybe let me summarize what the exercise says. So take two different points of Q bar. Now Q bar is not I'm not defining it as of course as the algebraic closure of Q, but as Q union infinity. Okay. So it's more boring, yeah, than the algebraic closure of Q. So take 2 points there, distinct, and well, of course, the naive addition is a rational number, even if one of them is infinity. So that's like the point. The point of this is that even if one of them is infinity, the naive addition is always a rational number, provided they are different. Second, each of the naive addition and naive subtraction are adjacent to both of them, provided, and here is of course not always, but here if here it is here is if here I have to say, of course, if R and S are adjacent.
That's an assumption.
Sorry. Yes. Yeah. You're yes. Yes. Sorry. Yeah. Thanks. Yeah. Yes. Okay. And now the thing is, the exercise is that not only they are adjacent to the naive sum, but they are also adjacent to the naive subtraction, which in a way kind of we already saw. This one is interesting. You know, we know that this one lies between the two of them. If they are rational, we know that this one lies between R and S, somewhere there, somewhere in the middle. Okay, and now the exercise is saying that this one lies on the other side, somewhere here, where of course here I pass through infinity and come back here. Okay, in particular they are different. They are not adjacent in the Faraday diagram, which means, you know, like at least I don't have this crossing between from here to the naive subtraction. So at least I don't have that. I know that this. I know by this one. By this one, I know that the naive subtraction is connected to them, and I know this. And so what this one is saying is that there isn't this crossing. And finally, like one that I find particularly beautiful is that now if you give me anything which is at the same time adjacent to R and S, then it has to be one of the obvious ones. So no strange things happening. So in other words, you give me R and S adjacent, then by definition they are adjacent to the naive sum. Then by the exercise, they are adjacent also to R minus S, which we in fact already did. This doesn't happen. Yeah, but also if you give me anything connected at the same time to R and S, it's only one of these two. So there aren't other strange adjacencies, simultaneous adjacencies to R and S. Simultaneous, right? I mean, of course, here there could be some other to R. Okay, so that's what the exercise says. It's quite easy. This is an exercise on determinants. Okay, so now let's talk about the fourth circles. Yeah, and so we take for each rational number written as reduced fraction, we consider a circle. So let me draw the real line. Yeah, and we take a rational number, R divided by S, written as, sorry, A divided by B, written as a reduced fraction. Yeah, and then what we do is we take the Euclidean circle HR with this diameter, tangent at this point. So it's one very specific circle, yeah, with yeah, this is 1 divided by B squared. So this means that the radius is of course 1 divided by 2B squared. And if you remember, this expression, this, you know, this radius already appeared in when we were talking about lambda lengths. And actually, like the horocycle tangent at a certain place with the corresponding with the Euclidean radius being equal to this was precisely one of those horocycles that we mentioned. And so what we are doing is we are taking a horocycle whose whose horocyclic distance to the horocycle at height 1 is precisely B. So that's what we are doing. So you know, so the horocyclic distance between this horocycle and this horocycle is B. But this is a lambda length, right? This is not hyperbolic length. This is the lambda length. So it's lambda length, which is this exponential of the signed distance divided by 2. The signed distance between the crossings. But of course here, signed distance, but of course here, B is greater or equal than 1, which means that that this diameter is at most 1, which means that signed distance is always taken with positive sign, because this horocycle never crosses this one. So in other words, this fourth circle doesn't cross the horocycle at height 1. Yeah, which by the way, we also say this one is the fourth circle based at infinity. Just kind of to kill two birds with one shot. So you see, this is H infinity. Okay, so those are the fourth circles, and then as you see, if I take an arbitrary rational number, it doesn't have to be at all tangent to this one. Doesn't have to be. Okay, but now some of them are, and this is a quite beautiful result. So take two rational numbers. Sorry, before going to the rational numbers, if I take an integer, you know, if I take an integer, let's say here m, which is m divided by 1 integer, then the fourth circle has diameter 1, so it is indeed tangent to this horocycle. Okay, that was not tangent, but no. So it's okay. I don't want to waste too much time. So for the integers, we do have tangency between the corresponding fourth circle and the fourth circle at infinity. And moreover, if you think about it, the radius is 1/2. So when I consider m plus 1, so this is 1/2. So when I consider m plus 1, it's also tangent. So here, never mind about the other one. Right? So at least I know that for each integer, the corresponding fourth circle is tangent to the fourth circle at infinity, and for two consecutive integers, their fourth circles are tangent to each other, which sounds like the basis of the recursion for defining the Faraday diagram. And the theorem says that that's exactly what happens all along the way. Yeah? So it says, if you give me now two rational numbers, we already dealt with infinity. We just dealt with infinity. So now take two rational numbers, written as reduced fractions. So the first thing is that they never cross. You know, the two fourth circles, they never cross. So they are either entirely disjoint or they are tangent. Yeah? If you think it cannot happen that one that one is inside the other, this cannot happen because they are both tangent to the real line. If one was inside of the other, they would be two fourth circles based at the same rational, but we have associated only one fourth circle. So I would say even this is true at the level of the disks, not only at the level of the circles. They are either disjoint or tangent, but they never cross. And then, as I said, there are no weird nests at all between them. Furthermore, they are tangent if and only if their base points are adjacent in the Faraday diagram. So this I find really beautiful. Okay, but not only that. When their base points are adjacent in the Faraday diagram, then what happens is that the Faraday edge connecting the 2 points actually passes through the point of tangency between the two fourth circles. So that's what this says. So in other words, the fourth circles configuration is completely compatible with the Faraday diagram configuration. Yeah, and of course it's orthogonal to both of them because of course it's orthogonal to this, tangents orthogonal, and then of course in the other point of tangency it's also orthogonal to them. Okay, the proof. Maybe I'm not going to read you the proof. It's basic algebra, basic algebraic manipulations. Yeah, so for this, for the proof, let's say of one and two, maybe I'm going to skip it today. Yeah. I don't want to because I have a lot of material. So just for the third one, once these two have been proved, yeah, let's assume that we already proved 1 and 2, and let's see the third one. So to prove 3, we assume that our two given rational numbers are Faraday adjacent, so that there is a Faraday edge, yeah. And then at this point, we have also proved that their fourth circles are tangent, yeah. And so this has been proved. Okay, and now we throw we draw the tangent Euclidean line, yeah, and then of course it crosses the real axis somewhere, and then we throw the tangent to the one on the left, let's say. Yeah. Then of course we know that that this distance is equal to this distance just by basic Euclidean geometry. right? Because we know that the configuration for the tangents is invariant under the Euclidean reflection through this line. So the line connecting this point, which is the Euclidean center, and the point from which I'm throwing the tangents. Yeah? So this is equal to this, and then by the same token, this is equal to this. Yeah, which means that when I draw the Euclidean circle with this radius, yeah, I pass through the tangency point and I land on the other one. But this one is precisely the Faraday edge. Done. So basic Euclidean geometry. Okay. Yeah, and then this is the Faraday diagram and the Euclidean and the fourth circles drawn simultaneously. So I don't know, I find it quite nice. I mean, you could call it some sort of sphere packing, two-dimensional sphere packing of the unit disk, let's say, well, of the disk, or of the upper half plane. Yeah, which means, which you see if you think in terms of lambda lengths, what we are saying is that that if we take two rational numbers, they are adjacent in the Faraday diagram precisely if the horocyclic distance between the two associated fourth circles is 0. If you want to kind of to do the exercise of thinking in terms of lambda lengths. Yeah. Okay. Faraday sequences, and this is this is an, let's say, this is going to be a slightly, it's a kind of another approach to constructing the Faraday diagram that allows to prove that what we obtain is a triangulation of the upper half plane. So far, our first definition of the Faraday diagram recursively, it says, okay, every time you have an adjacency, take the naive addition. But then taking the naive addition, since we are adding the denominators, the denominator may increase a lot. Like, for example, here these two are adjacent, and then in the next step, the denominator is going to be 13. So it's what? It's 11 divided by 13 in the next step. Which means, you see, the denominator increased a lot. I mean, a lot in the sense that you see, it's kind of, it didn't increase by 1 only. Okay, now for the nth Faraday sequence, what we take is all the rational numbers that can be written with denominator at most n. You know, I mean, with positive denominator at most n. Yeah. And here a priori I don't even say that this one has to be reduced, but that's irrelevant, because if it can be written like this with positive denominator smaller or equal than n, then its reduced expression also can be written that way. So it's irrelevant in this definition. Yeah, and then what we are seeing here, for example, is let's say the fourth Faraday sequence. The fourth Faraday sequence, we are seeing it here like this. So this is the fourth Faraday sequence. Well, at least between 0 and 1. Okay. Now, something to notice is that, for example, these two are in the fourth Farey sequence, and their naive sum is in the next one. Yeah, but for instance, this one and this one are in the fourth Farey sequence, but their naive sum is not in the next one. So this means that the nth Farey sequence is not equal to the nth recursive step in the definition of the Farey diagram. Yeah, and actually, what seems to be happening is that the nth Farey sequence is somehow contained in the next one. Not in the next one. Sorry, the nth Farey sequence is contained in the nth recursive step of the Farey diagram. That seems that seems to be what is going on. It is indeed, but it does require some proof.
Sorry.
No, that's not the same.
Sorry?
Yeah,
Just,
maybe
I think it's the same, so go ahead.
Or what did I say?
I mean, just this observation is F8 inside E8. I mean, E8 is pairs of numbers since it's the edges.
You're right. Yes. Yeah. I meant here V. Excuse me. Yes. Yeah.
Is it contained different or not contained?
It's contained and different. Yeah. Sorry. Yeah. Contained and different. For me, it's this, and not contained would be yeah. 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 So yeah. No. I mean contained but not equal. Yeah. And this is what always happens. That but it requires a proof. That so at least intuitively it looks like to construct, you know, Fn plus 1 from Fn. Yeah, okay, no, this is actually, I have to prove it, but let me tell you what is going to happen. What is going to happen as a corollary of the next theorem is that the difference between Fn plus 1 and Fn is that Fn plus 1 can be obtained from Fn by taking, for Fn, between consecutive members, naive sum, and then if the denominator is greater than n plus 1, discard it. If it is not, include it. And that is how you obtain Fn plus 1 from Fn. That is going to be what happens. But for that, one needs this theorem, which is, you see, if you give me two rational numbers, then they happen to be consecutive somewhere, you see, so in some Farey sequence, if and only if the determinant is equal to 1. And then the proof is actually very similar in nature to what we have been doing. Do I want to stop and say and actually go into the details? Let me think. Yeah, I think I do want to say something. Maybe not read the whole calculation, but do say something. So by induction, because F1 is Z, okay, Z union infinity. That's according to what I defined above. Yeah, and then one just checks, right? I mean, this we know that this determinant is 1. Where, of course, here I'm not writing plus or minus 1 because I'm already writing the larger as first column. So that's why here there is no plus or minus 1. If I write them, you know, kind of randomly, then I do have to write plus or minus 1. Okay. The inductive base is obvious. Okay? This we have said many times already. Inductive step. So we take we fix Fn, yeah, and assume by induction that for every pair of consecutive terms, we have determinant 1. Okay, and then analyze. First of all, since they are consecutive in Fn, when I since they are consecutive in Fn, when I consider their naive sum, and the denominator being b plus d, sorry. Sorry. If I take two consecutive terms, in Fn, of course, no other rational number between them belongs to Fn. In particular, their naive addition is not in Fn. So this means that the denominator of their naive addition is bigger than n. So that's what I'm saying here. Which of course means this. Okay, and now I have two cases. Either my two given consecutive terms of Fn are remain consecutive in Fn plus 1, or they don't. If they do, then I already know that the determinant is 1, so I don't have anything. I have nothing to prove. Their determinant is 1. Otherwise, there is someone in between. So if they are not consecutive in Fn plus 1, there is someone if in Fn plus 1 in between them. Okay, and one shows that that their naive sum, which is in between them, belongs to Fn plus 1. So if these two are consecutive in Fn but not consecutive in Fn plus 1, one proves that their naive addition is in Fn plus 1. So in other words, it's a witness that they are not consecutive in Fn plus 1 because their naive addition lies in between. And moreover, one proves that it is the unique element of Fn plus 1 that lies between them. And this is done, through basic algebraic manipulations. So maybe I'm not going to read the whole algebraic manipulation. I'm just going to say, look, if they are not, since they are not consecutive in Fn plus 1, there is some fraction with this denominator between them, because they are not consecutive in Fn plus 1. But you see, since they are in consecutive in Fn, this fraction cannot be expressed with a smaller denominator, which means this one is already a reduced fraction. Okay. And then through algebraic manipulation, one goes blah 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 blah. So the fraction, any fraction in between, has to be the naive sum through some basic blah blah. Okay. Okay. And then the determinant between this and this one, which is the next one in Fn plus 1, we know is 1. And the determinant between this one and the next one in Fn plus 1, which is this, we know that is plus 1. That is 1. Always writing the bigger algebraic, the bigger rational number as the first column. Okay. So what do we know? we know that that whenever we take two consecutive in Fn, we know that they are either remain consecutive, and we knew that by induction that the determinant was plus or minus 1, or we know that there is exactly 1, and we know that there's the property of determinant plus or minus 1. And this is, we do it for every two consecutive. We have indeed that for Fn plus 1, any two consecutive satisfy that the determinant is 1. Done. Okay, and conversely, for this is also very elementary. I'm not going to I'm not going to like read it for you. So this you can just consult in the notes. What I wanted from that proof is that then we know how to construct, let's say, Fn plus 1 from Fn if they ask me, right? I mean, if they ask us, okay, if I give you Fn, how do you construct Fn plus 1? Now we know how it is constructed, right? And since it was a determinant equal to 1 condition, then we also know that if you give me two rational numbers, they are consecutive in some Fourier sequence, in at least one Fourier sequence, if and only if they are connected through a Fourier edge. Okay. Right, and now one can prove that the Fourier diagram actually triangulates the hyperbolic plane. And one proves that no pair of distinct Fourier edges cross in the hyperbolic plane in U, right? I mean, they may share a tangent. They may be tangent, but and the point of tangency can be a real number. This can happen, but they do not cross in U, in the upper half plane. Okay. So in other words, two different Fourier edges may have common points, but only in R bar, not in U. And second, the Fourier diagram triangulates, and more precisely, one can say exactly what are the ideal triangles. They are of the form, take a Fourier edge, yeah, and then take the naive sum of the two vertices of that edge, and take the hyperbolic convex hull. That's an ideal triangle. Yeah. That collection of ideal triangles is precisely the triangulation of U one obtains. Okay, so that's the statement of the theorem. So let me maybe argue why no pair of distinct edges cross in U. So let me think. Yeah, so I would say that one way to proceed is by induction on the construction of the Fourier diagram. At the very beginning, when one only has the integers and infinity, those edges, between consecutive integers. So maybe let me write it. So when one only has the integers, and infinity, one has these edges. These Fourier edges, which do not cross in U. So what's up? No?
Since I don't know what really doesn't mean triangulation, I will ask more precisely what is more, it is a triangulation, not only triangulates, what is the meaning of ideal triangulation
Yeah.
more than the first.
Yeah. So remember that an ideal triangle is the hyperbolic convex hull of 3 distinct points at infinity. Right? So I take 3 distinct points at infinity. Their convex hull is an ideal triangle. So let me see if I can maybe if the program is still there. Convex hull, geodesic segments. Oops, sorry. Yeah, okay, so that's a hyperbolic triangle, but it's not ideal. Right? But now something like this, I mean, that's still not ideal. That's still not ideal. But this, yeah, but now that's an ideal triangle. And now by this statement, yeah, that this set of ideal triangles is an ideal triangulation of U. I mean, first of all, every such triangle is ideal. So for every such triangle, the 3 vertices are points at infinity, which is obvious, right? Because like lives in R bar, lives in R bar, lives in R bar. So that's the easy part. The hard part is that if you take the union of all the Farey edges and you take its complement in U, so you delete them from U. So what you obtain is a certain open subset of U, right? And by this statement, what I mean is that every connected component of that complement is an ideal triangle, and it's like one of these, yeah, of course, with the boundary deleted, because I took the complement. That's what I mean. That the complement of the Farey edges is a triangulation in the sense that each connected component is an ideal triangle. Yeah. Mm-hmm. Okay. So now for the first statement that the Farey edges don't cross inside U. I think that one way to proceed is by induction on the recursive construction of the Farey diagram, because you see, like if in each step I never have crossing edges, then in the limit I never have crossing edges. Right? I mean, if 2 edges cross, it's because after they were constructed, they crossed in some finite step. Right? Okay. So, in basis of the induction, that the part that was kind of God given, that the edges don't cross. But it's just clear, right? That they don't cross. Okay. Like you say, even first one more step. We have to add the naive additions, which in this case they are very easy to compute, right? So for the first recursive, the first step of the recursion, which would be add these vertices and these edges, where all these new vertices have denominator 2, are the midpoints between the integers, between consecutive integers. And I think it's still obvious that there's no crossings. Okay. And then inductively, one says, okay, so let's, and yes, and then one more thing is, notice that here, what I have actually is actually F2, the second Farey sequence. So at least and it's not 1/2. Sorry, it's whatever. 1 plus 1 plus 1/2, 2 plus 1/2, etc. 3 plus 1/2, etc. Minus, yeah. But what my point is, here, at least after the first recursive step, we do have F2. Yeah? So the recursive process for the Farey diagram and the recursive process for where did I put it? For the Farey sequence, this one. At least in the first step, they are the same. They start differing after. Yes, and now the inductive step is going to be yes, not on the recursive step of the construction of the Farey diagram, but in the recursive step of the construction of the Farey sequences. So here, because one has more control there. So for the inductive step, let me see if I can say it more or less quickly. Now let's say that we have Fn. Yeah, let's say that we have Fn, and we have Fn, and we also have Fn plus 1. So let's say that we have two consecutive here, and they either remain consecutive or not. Let's say that they don't remain consecutive. So this in yellow is in Fn, and let's say in I don't know, this it's in Fn plus 1. Yeah, so this is in Fn plus 1, but not in Fn, while R and S are. Yeah, so we know that we do have this Farey edge, and we do have these Farey edges. Yeah, these are new ones, right? So maybe let me write them in this. I mean, yeah, yeah. So those are the new ones, and inductively, I'm assuming that any two edges connecting elements of Fn do not cross. And now I want to prove that any two edges connecting elements of Fn plus 1 do not cross. So I take an edge. I take two edges, and then these two edges, either they were already edges in Fn, in which case I know they don't cross, or they are two new edges, or they are one new, one old. So I only really need to analyze the situations new, old, new, new. So new, let's say new, old, let's say, So the kind of what makes it a bit, at least for me, challenging is that let's say new, old. So I have to compare one of those that I have, one of these that let's say that I picked arbitrarily, with a yellow one. But then the yellow one may be somewhere here, right? Which of course, if I draw it that way, of course it doesn't cross it. But the point is that it shouldn't be like this, right? Okay. So somehow the idea is, but of course, then if I draw it like that, then you are going to say, yeah, but then two yellow cross. Okay. So could it be like this? You know, that's kind of the thing. But then if you think about that, you see, somehow this means that these were not consecutive in Fn, because there's this guy. I mean, so more formally, in order to cross this one endpoint has to be in this interval, and the other endpoint outside. Okay, so pick the point in that one, and use the fact that it was an old edge to say, okay, then these two were not consecutive in Fn. Okay, so this proves that new against old don't cross. New against new. New against new. You see, this means that again, new. Let's say this new one against another new one. So this means this one, which lives in Fn plus 1, it's also between these two, but we said the only one between them was this guy. So. Okay. So at least we have this, and the fact that they triangulate. And that's probably already obvious. You see, now if you give me an edge, I would say that now it's more or less easy at this point. If you give me an edge, an edge not involving infinity, then I know that the naive sum is connected to both, the naive subtraction also, and no one else, to these guys, right? And then no other edge crosses this configuration. So this means that somehow every edge sits really as a diagonal in an ideal quadrilateral. So I think by now it's already clear. Yeah, that every connected component of the complement of the Farey edges, of the union of the Farey edges, is one of these. Yeah. Now, notice. Notice if I take naive addition between an integer and infinity, with infinity written as 1 divided by 0, then the naive sum is the next one. And the naive sum is the next one. The naive sum with infinity, the next one. Whereas naive subtraction, this one with infinity written this way, is translation to the left. So that's something I wanted to say. One second. The thing is, Yeah, I mean one of those points where somehow I think it's already obvious, but somehow I'm not sure if I'm not letting just the intuition, take the better of me. But I think so, right? I mean, if I take one such, bless you, ideal triangle, then I know that nothing else crosses it. So it is a connected component of the complement, right? No, yeah. Okay. Yeah, okay. And then if you remember, we started with something that was like, which is like, why are you talking about, this approximation of an irrational number by rationals? And it's something really nice. I mean, that I find really, really, really beautiful. So draw the real line, or if you want, R bar, and take an irrational number, alpha, and then draw the vertical line through that irrational. So this is. So in other words, the geodesic connecting it to infinity. Well, that doesn't look very straight. So infinity is somewhere here, and then the exercise is that this one crosses infinitely many Faraday edges. That I'm tempted to just solve it. I mean, what happens if it intersects only finitely many? If it intersects only finitely many, I mean, there is one that is kind of the closest one. I mean, not the closest one. That if I orient from infinity to alpha, if they were only finitely many, there would be a last one. Okay, then there is a last one, but then these two guys have a naive addition. Right? But then it crosses one more. Okay, so quite easy. Right, and then for those for those infinitely many, so now consider the sequence of all the ones that it crosses. Yeah, I don't want to draw something too intuitive, but yeah, no. Yeah. No. So yeah, what I'm going to do is allowed. The picture I'm going to draw is allowed, namely. So take, I don't know, the first one. The first one it crosses, which, if I'm not mistaken, it has to be a Faraday edge connecting integers, because it comes from infinity, and those are the outest ones. Right? So it has to be that way. And then, but then since it's an irrational, it's not the naive addition of them. Right? So the naive addition is somewhere in between, but it's not alpha. Yeah? So I'm kind of repeating the argument why there are infinitely many Faraday edges crossed by the white vertical line. But my point is this, that then I can consider, that from this, take this one, the one that is crossed, and then between this and this, and I have sum, and then either you see, it has to cross one of the two. So it's either this one, if the naive addition is on the right, or it's this one if the naive addition is on the right. Yeah. So what I see, let's say that it's the second case. You see that the naive addition is this one here, And then let's say that the naive addition between these two, let's say that is again there. Yeah, and then let's say that at some point there is a change, so that now it's this one, and then etc. Yeah, and then at some point there is a change. So my point in doing this is that it looks like a sequence of fans, right? It's like a fan of things like this, and then a fan of things like this, and then a fan of things like this, etc. Okay. And so what? Yeah, and then what I can do is you know, in let's say between two consecutive ones, consider the fourth circle. You know, I mean, these don't look orthogonal to R anymore, but yeah. But so now take this one and the next one. So which I know is actually I know that they are tangent here, but okay. But so I'm going to, yeah. But so this point is this point. Okay. Yes. Now let's say that this is right, and now let's say that this one is I don't know, P divided by Q, and this the next one. The next one, I don't know how to. It's this one, but but you see, the first thing is that if they are consecutive, consider the open disks, the open four disks, and what I say is that that when you project the union of those open disks to R, it contains alpha. Why? Because they are tangent. The circles are tangent. So the only possibility for not containing alpha is that the tangent is vertical and falls precisely into alpha. But if the tangent is vertical and falls precisely into alpha, that means that alpha is the midpoint between them. But then alpha is rational. Okay. But then this means that, but then this one has radius 1 divided by 2q squared, right? So this means that for one of them, so alpha lies in the image of the open disks of any two consecutive ones. So this means that it lies in the shadow of one, or in the shadow of the other, or maybe in the shadow of both. I don't know. But for the one where it lies under the shadow, it's the distance to the rational number is less than 1 divided by 2q squared. So, and there are infinitely many such, because this I could do it, you know, I can do it infinitely many times. This argument. This is better than this. This is not just 1q squared. It's 2. Which, you see, the first approximation we saw was 1 minus pq. Yeah, 1, 2, q, which is the one that we have known forever, right? Because the rationals are dense in the real numbers. This one is better. Yeah, my time is up, so I haven't even started with this. But at least, you know, we saw some I really think it's a spectacular application of the Faraday diagram. Okay, so see you tomorrow.